Welcome to this explainer. I am absolutely thrilled you're tuning in today because we are undertaking a true masterclass in thermodynamics. Look, I know physics formulas can sometimes look super dry or intimidating on the page, but today we're going to transform them into a highly logical, completely practical toolkit for solving real-world thermal problems. Whether you're trying to figure out why your morning coffee cools down so frustratingly fast, or you're calculating the precise energy required to melt a solid block of ice, you're going to walk away from this explainer with a really deep, intuitive understanding of how heat truly behaves. And real quick before we jump in, make sure to subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCS to excel in your Cambridge examinations. Let's get started. Okay, so here is our structural roadmap for today. We're breaking this down into 4 clear steps. First, the baseline, where we'll look at temperature scales. Second, heating up with specific heat capacity. Third, changing states through latent heat. And finally, the grand synthesis, where we'll solve some complex thermal exchange equations together. All right, section 1, the baseline. Let's get our temperature scales sorted out. So, before we can do any actual math, before we calculate a single joule of energy or heat transfer, we absolutely must be speaking the same language when it comes to temperature. If our starting metrics are off, the whole calculation basically crumbles. Notice the contrast between the 2 main scales we use in physics. On the left, we've got the Celsius scale. Now, this is empirical. It's designed perfectly around the fixed freezing and boiling points of water. It is fantastic for knowing if you need a jacket outside, but it definitely has its limitations in the lab. On the right, we have the thermodynamic scale, measured in Kelvin. This one is theoretical, and it's completely independent of any specific substance. It starts all the way down at absolute zero, literally the lowest possible temperature in the universe. But here is the brilliant part. 1 degree on the Celsius scale is exactly equal in size to 1 Kelvin. The steps are identical. It's really just the starting line that's different. Because the steps are the same size, the crucial thing we need is a bridge between these 2 scales. And that bridge is the number you're looking at right here, 273.15. See, because the Kelvin scale starts at absolute zero, water actually freezes at 273.15 Kelvin, which we know corresponds to 0 degrees Celsius. So to convert any Celsius temperature into the thermodynamic Kelvin scale, all you have to do is add 273.15.
Let's look at a super quick example from the source material just to lock this in before moving on. Say we have a liquid measured at 35 degrees Celsius. Step 1, identify that Celsius value, which is 35. Step 2, we just add our conversion number. The source uses 273 here, just dropping the decimal to keep it to 3 significant figures for simplicity. Step 3, 35 plus 273 equals 308 Kelvin. It really is that straightforward. Okay, now that we have our baseline established, we're ready to talk about the fun stuff, energy.
Section 2, heating up. Time to dive into specific heat capacity. Have you ever noticed how on a really hot summer day, the beach sand can absolutely burn your feet, but the ocean water right next to it is still freezing cold? I mean, they're both sitting under the exact same sun, absorbing the exact same heat. So why the huge difference? Well, it all comes down to specific heat capacity. Represented by the lowercase letter c, this is the thermal energy per unit mass required to raise the temperature of a substance by exactly 1 degree. Now, pay close attention to that word specific. In physics, whenever you see the word specific, it almost always means per unit mass, in this context, per kilogram. So we are measuring exactly how many joules of energy it takes to heat up 1 kilogram of a material by 1 Kelvin. And this table right here brilliantly illustrates why materials react so differently to heat. Just look at the stark contrast in these numbers. Water has a massive specific heat capacity of 4,200 joules per kilogram per Kelvin. It is literally a thermal sponge. You have to pump a tremendous amount of energy into it just to raise its temperature a little bit. Now look down at copper. It's only 390. That means it takes more than 10 times the energy to heat a kilogram of water than it does to heat a kilogram of copper by the exact same amount. This is exactly why metals heat up so incredibly fast compared to liquids. So how do we actually put this into practice? We use this incredibly elegant mathematical relationship. Delta Q equals mc delta theta. Let's break that down. Delta Q is the total thermal energy you're supplying. To find it, you just multiply the mass of your object, that's m, by its specific heat capacity, that's our c, by the change in temperature, which is delta theta. So if you ever want to know the exact energy needed to heat up a block of that copper from our last slide, you literally just plug the mass, the 390 specific heat capacity, and your target temperature change right into this equation. It's a real game changer for solving thermal problems.
Moving on to section 3, changing states. Let's talk about latent heat.
Things start to get wonderfully strange when materials actually change their phase, like melting from solid to liquid or boiling from liquid to gas. This introduces the concept of hidden heat. In fact, the word latent literally means hidden. Specific latent heat, which we represent with a capital L, is the quantity of heat per unit mass required to change the state of a substance at a constant temperature. Now, I want to emphasize that final phrase, at a constant temperature. Think about it. If you put a pot of boiling water on a stove and stick a thermometer in it, you are actively pumping massive amounts of thermal energy into that water from the burner. But the thermometer? It stays locked exactly at 100 degrees Celsius. The heat is hidden because it's not actually changing the temperature anymore. It's using all that energy to change the physical state of the matter itself.
What is truly fascinating here, and you can see it clearly on this chart, is the sheer scale of the energy involved, which totally depends on which state change is happening. The specific latent heat of fusion, that's melting solid ice into liquid water, takes about 330 kilojoules per kilogram. Pretty significant, right? But then, look at the specific latent heat of vaporization, turning that liquid water into steam. It takes a staggering 2,260 kilojoules per kilogram. The visual disparity here is just massive. So why is there such a huge gap? Why does vaporization take so much more energy than melting? Well, when you melt ice, you're really just overcoming the rigid forces holding the solid structure together. But the molecules themselves stay pretty close. The volume barely changes at all. But when you boil water into steam, you are violently separating those molecules until the forces between them are essentially negligible. Plus, the volume completely explodes. Just 1 cubic centimeter of water becomes about 1,800 cubic centimeters of steam. That massive expansion requires extra thermal energy simply to push back the entire weight of the Earth's atmosphere. It's working incredibly hard. And by the way, if you're enjoying these deep dives, remember to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.
Finally, Section 4, the grand synthesis. Let's bring it all together with thermal exchanges. So, what actually happens when we mix hot things with cold things? The answer lies entirely in this core principle from our source material. The thermal energy gained by the cold object is equal to the thermal energy lost by the hot object. Assuming we're in a perfectly insulated container where no heat escapes into the room around it, this is the absolute golden rule of thermal equations. Heat lost equals heat gained. It is the law of conservation of energy functioning in its purest, most mathematically useful form. Let's test this golden rule with a real-world scenario directly from the text. Imagine you take 0.30 kilograms of near-boiling water sitting at 95 degrees Celsius, and you mix it with 0.50 kilograms of room temperature water at 20 degrees Celsius. Obviously, they're going to eventually settle at some middle equilibrium temperature. But how do we find that exact final temperature? Let's walk through the math together. It's really like solving a puzzle. Step 1, we simply set up our word equation. Heat energy lost by the hot water equals heat energy gained by the cold water. Step 2, we drop our specific heat capacity formula. Remember, mc delta theta on both sides. On the left side, for the hot water, the temperature change is 95 minus our unknown final temperature. On the right side, for the cold water, the change is our unknown final temperature minus 20. And because they are both water, that specific heat capacity variable C, the 4200, is the exact same on both sides. Step 3, now it just becomes basic algebra. You distribute the numbers, you isolate your unknown final temperature on one side, and you beautifully arrive at 48 degrees Celsius. That's your equilibrium. Now, the most advanced problems you're going to encounter simply layer the tools we've already learned today. For instance, what if instead of mixing water with water, you drop a handful of solid ice cubes into a warm drink? You just break it down into logical steps. First, the warm drink has to lose energy to actually melt the ice. That's your latent heat equation, M times L. But wait, you aren't done. Now you have freezing cold 0-degree water sitting right there in your warm drink. So the drink must lose even more energy to warm up that melted ice water to the final equilibrium temperature. And that's your specific heat equation, mc delta theta. You literally just sum them up. The total heat lost by the drink equals the heat gained melting the ice, plus the heat gained warming the resulting water. See? It all connects. Before we wrap up, I want to leave you with one final, provocative question, derived straight from our source material's end-of-topic questions. Both boiling water and steam can exist at exactly 100 degrees Celsius, right? But knowing what you now know about the massive energy required for vaporization, why is a burn from 100 degrees steam significantly more serious than a burn from 100-degree boiling water? Just think of all that hidden latent energy locked inside the steam, just waiting to be violently released the second it condenses on cooler skin. It's wild to think about. Thermodynamics isn't just formulas on a page. It's the intense, visceral reality of the physical world all around us. Thank you so much for joining me for this explainer. I hope you found it as fascinating as I do. Keep questioning, keep calculating, and please, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. I'll see you next time.